Okay, so I'm copying our last one that we did together here. So we had that whole polynomial, and we were going to divide that by x plus 1. Okay. So what we just talked about was, if you're dividing by something that is a binomial, then we can take what we have in this polynomial division and use synthetic division instead. Okay. And the way that it works, we have this, it looks like a backwards L, but it's kind of like a little box. And in that box is going to go what we had in this part of our division, so our divisor. But instead of x plus 1, what goes in that box is the number that makes this 0. So what number, when you plug it into x plus 1, makes it 0? -1. Okay. So in that little box, we're going to put -1. And then next to it is going to be what we're dividing out of, okay, which is this big long polynomial. But instead of having all the x's, really all I need are the coefficients. Because if you remember all the work that you guys were doing in that long division, really it was just the coefficients we were working with. As long as we kept them in order, in the right places, so that they all lined up right, then it would still work. So I'm going to take all of those off of there. So 4, -2, 1, -1, and 5. And we just write them straight across. And just make sure they're nice and spaced out. And then you're going to skip a line and then draw a line. Okay. So here's how it works. First number, whatever it is, just drop it down. And then we're going to do that multiplying around step. So -1 times 4, -4. Okay. And then straight down there, because I switched the sign on this to -1 instead of subtraction, now we just add them. So -2 plus -4, -6. -1 times -6, 6. 1 plus 6, 7. -1 times 7, -7. -1 plus -7, -8. -1 times -8 is 8. 5 plus 8, 13. So take a look at those numbers. 4, -6, 7, -8, 13. And look at the answer to that last problem that we did. What do you notice? Yeah, I know. Trying to make it exciting again. Those numbers are the coefficients of your answer of the last one you did. And not only that, this 13 at the end, that's your remainder. And so usually we put a little bar down like this to kind of separate them. But yes, here's your answer. Here's your remainder. Now, when you're writing your answer, you got to put all the x's back on them. So how do we know what x, where's the x squared, where's the x to the third? How do we know which is which?
Start with the highest one, subtract degrees.
We knew it was an x to the fourth to begin with. That had 1, 2, 3, 4, 5 terms. Now we're down to 1, 2, 3, 4. So that should be an x to the third polynomial, a degree 3. So we have 4x to the third minus 6x squared plus 7x minus 8 plus 13 out of x plus 1. Same answer, much quicker. Okay, that's synthetic division in a nutshell. Now, the only thing that I think you guys are probably going to struggle with this is, again, remembering placeholders. If there's a missing term somewhere in the middle of a polynomial, like there's no x squared term, there's no x to the third term, whatever, then you're going to have to put those zeros in there when you do this too. Okay, otherwise you're not lining things up correctly, and it's not going to all match up the way it's supposed to. So just be careful you're not forgetting your zeros when you do that. But it works. Okay, so how are we going to use this stuff with all of our finding zeros? Well, we're going to do a little bit of it here today before we're done. And the first thing I wanted to talk about was the factor theorem. All right, factor theorem says f of x has a factor x minus k if and only if f of k equals 0. Okay, so that's the definition, but I'm going to put in here, which means if divided, it has a remainder of 0. And this is something we're gonna go back to this a lot, because a lot of what we're going to be looking at is checking to see, do we have zeros or not? I got this thing, I think it's a 0. I got this thing, I think it's a factor, and I want to try and work my way through it and use some synthetic division again and again and again to check a bunch of them. Okay, so there's this key connection here that if you have a factor, you have a 0. Okay, so kind of the big idea here is if x minus k is a factor, then k is a 0. Now there are other words that we use for 0 like solution, x-intercept, all that stuff. Okay, we're going to call them zeros for now. But if x minus k is a factor, then k is a 0. Okay, so let's use that idea and see if we can figure out how we can use synthetic division to answer the following question. Let's see. So is x minus 3 a factor of 2x to the third minus 3x squared minus 5x minus 12? So what am I ultimately going to do to check that then? Yeah. Divide them and then look for what? Look for 0. Look to see if the remainder is 0. If the remainder to the division is 0, it's a factor. Because think about it. What does a 0 remainder mean in a division problem? It means that the number goes in evenly, right? If something is a factor, isn't that exactly the same thing? A factor is something that goes in evenly into a polynomial. We're talking polynomials instead of numbers, but it's the same idea. It goes in evenly. Okay? So let's do the division, see what we get. So if it's x minus 3, that means 3 is going to go in the box. Then I'm going to take my coefficients here, 2, negative 3, negative 5, negative 12. And let's do that synthetic division. So bring down the 2. 3 times 2 is 6. Add those up, it's 3. 3 times 3 is 9. Add those up, it's 4. 3 times 4 is 12. Negative 12 and 12 is 0. So, do we have a factor? Yes, indeed. Yep. So we know x minus 3 is a factor. So we actually know a 0 to the function as well. What number has to be a 0 to this function? 3. Just like when you guys had quadratics and you would factor it, and then take your two factors, set them equal to 0, and so solving each one of those would give you the zeros. Well, I didn't actually factor this thing, but I did find out that this particular x minus 3 was a factor, which then allowed me to know that x equals 3 was a 0 that goes with it as well. Okay, so I talked about before there's going to be some problems where you can't factor. However, you can do some synthetic division to check, to try out a bunch of them, and as soon as you get a remainder of 0, then you have one you can use. Yeah? You could also do that. Yeah. If you think that's easier, I don't know, maybe. In this case, let's say you didn't have a calculator to use. Might not be at that point. I don't know. I mean, 2 times 3 to the third minus 3 times 3 squared minus 5 times 3 minus 12. I don't know. Some people can do that in their head pretty quick, but yeah. Okay, then yeah, absolutely. And that's an important point, though. I mean, there is that connection, too. F of 3, you know, this is what the factor theorem was saying, too, is that if you plug the number in, it should come out to 0. And so, yeah, if you feel like that's an easier process for you, 3 to the third is 27. 2 times 27 is 54. That's 18. 3 squared is 9. Oh, 27. Yep. Minus 15 minus 12. So 54 minus 27 is 27. So, yep, so that's 0. Yeah. Okay, so, I don't know. Both are pretty simple. I think if you end up with polynomials that have a degree much larger than 3, though, you're probably going to want to go with the synthetic division instead, because then you got to try and, like, you know, raise things to the 4th and 5th powers, and it gets a little messy. But yeah, that one's all right. All right. So that is the factor theorem. There's also what's called the remainder theorem, which is related to the factor theorem. And so this is kind of like the general case for everything, not just checking for factors, but so let's make sure I'm saying this the right way. So if f of x is divided by x minus k, then f of k is the remainder. Now, do you see how the factor theorem is actually just kind of a specific case of the remainder theorem? It's really doing the same thing, right? It's using the remainder theorem where the remainder happens to be what? 0. Okay? But it's saying the same thing. If you plug the number into the function, whatever you get out at the end should be your remainder. Oh, and look, if it's a factor, that should be 0. Okay. So it kind of works the same way. So if you know, the use of the remainder theorem, I suppose, is if you're really wanting to just know, does it have a remainder or not, or if it does, what is the remainder? And if it's easier to just plug the number in, you can do that. Okay? I'm not going to do much more with that, but that's the idea. The factor theorem exists because this remainder theorem does.